Good afternoon. This is Unit 7, Day 8, Notes, Complex Zeros. And we're going to be doing a little bit of graphing in this section of notes at the end, so you will want some graph paper. Most of the rest is algebra and drawings. Okay, so to understand where complex zeros fit into what we're learning, you need to know a little bit about the imaginary unit. So the imaginary unit was invented to solve the problem x squared equals -1. Of course, there is no x value that you can square and get a negative. So this answer is undefined in real numbers. Not possible to solve. So what mathematicians decided to do is they said, okay, what if we create a temporary answer, and maybe at the end, this temporary answer will eventually come around and become real. It's a pretty cool idea, actually. So they said, all right, if we were to solve this normally, we would square both sides. 2 x's, 1 comes out, and then we've got the square root of -1. Then they invented something called the imaginary unit, which was an italicized I, and they said, okay, we're going to let I be a special letter, and it's equal to the square root of -1. Of course, if you square it, then I squared would be -1. So they invented the imaginary unit to solve the problem. So, sorry, that should be an x. 2 x's, 1 comes out. Basically, you end up with x equals plus and minus I, the imaginary unit. So, one thing you need to know about solving with imaginary unit, first of all, standard form of a complex number is a plus or minus bi, where the real part comes first and the imaginary part comes second. So technically, all numbers are complex because, for example, I can write the number 2 as 2 plus 0i. I can write the number 3i as 0 plus 3i. So basically, all numbers are complex. In mathematics, though, typically when we refer to a complex number, we are specifically talking about numbers with the imaginary unit. But technically, all numbers are complex. So how does this fit into what we've been learning? Well, we've been learning rational zeros theorem. So the question is, what does rational zeros theorem get us, and what does it not get us? Okay, so rational zeros theorem only gives us, well, rational zeros, which are any numbers that can be shown as some number a over some number b. So, for example, 2, 1/2, 4 over 1. Those are all examples of rational zeros. What it does not give us, so it does not provide irrational zeros. It does not provide irrational zeros, which would be numbers like pi or anything with a radical in it, because that's a non-repeating, non-terminating decimal. Non-repeating, non-terminating decimal. Anything that is a non-repeating, non-terminating decimal is irrational. Now, rational zero theorem does also not give us complex or imaginary zeros. So anything like 2 plus 3i or 6i or anything like that, it simply does not provide us. So where then do those things fit into the process? Okay, so here's where the process is. So number 1, you use the rational zeros theorem to find all rational zeros. Number 2, divide those zeros out. So number three, what's left? And whatever's left, you have to then solve. So this is where you might use, we assume that's what's left is not factorable, but you try to factor it, of course. If it doesn't factor, you can use the quadratic formula. And from the quadratic formula, that's where you get your irrational zeros and your complex zeros. It's at the very end of the process. When you've divided out all the rational numbers you possibly can, what's left then you can get out of quadratic formula, which is why most of our problems will give you just enough rational numbers that it will get you down to a quadratic, something in the form ax squared plus bx plus c, and then you'll use quadratic formula. All right, we're going to get back to that idea. Roman numeral 2, though, we need to be able to do some basic complex operations. So basic complex operations. And we've already practiced these at least once this year, but we're going to review them briefly just to make sure you've still got it. I already told you what standard form was. So let's just do some examples. We're going to add 2 plus I plus 3 plus I. Okay, so when you add reals to reals. 2 plus 3 is 5, and imaginaries to imaginaries. I plus I is 2I. You always end in standard form, which is A plus and minus BI. Okay, example 2. Subtract. Let's say you've got 13 plus I minus the quantity, negative 5 plus I. So you're going to distribute the negative just like you would normally. So 13 plus I, distribute, plus 5 minus I, and then add the reals. 13 plus 5 is 18. Add the i's. I minus I is 0. So if you have to answer in standard form, it would be 18 plus 0i. If they're not specific, then you can just say 18. All right, example 3, we're going to multiply. We're going to multiply 2 plus I times 4 plus 3i. Now, in the beginning, multiplication is just like normal. You're going to distribute the 2, distribute the I, and add up. So let's do that. 2 times 4 is 8. 2 times 3i is 6i. I times 4 is 4i. I times 3i is 3i squared. Add like terms. So 8 plus 10i plus 3i squared. Now, the rule for imaginary numbers is you never end with I squared. You always replace it with -1 because that's what it's equal to. So this right now is 3 times I squared. So we're going to replace the I squared with a -1, which is 3 times -1. So 8 plus 10i minus 3. And then finish out the problem. 8 minus 3 is 5 plus 10i. Of course, I should be boxing my answers. There we go. Okay, that's multiplication. All right, example 4. We're going to do division. We're going to do 4 minus I divided by 5 plus 2i. Now, division with complex operations isn't like polynomial long division. It isn't. Division basically is to eliminate i's in the denominator. You can't have i's in the bottom. So in order to get rid of the i's in the bottom, you're going to use a concept called complex conjugates. And what complex conjugates are is if you have one number, a plus bi, its conjugate is a minus bi. So sometimes they're called a complex conjugate pair. But the characteristic that you're interested in is if you multiply complex conjugates, so a plus bi times a minus bi, the answer is real only. It gets rid of the imaginary number. So we're going to use complex conjugates to get rid of the I on the bottom of this equation. So the complex conjugate of 5 plus 2i is 5 minus 2i. Of course, if you multiply the bottom by 5 minus 2i, you have to multiply the top by 5 minus 2i. Now, usually you're going to want to multiply in a line. 4 times 5 is 20. 4 times negative 2i is negative 8i. Now distribute the next one. Negative I times 5 is negative 5i. Negative I times negative 2i is positive 2i squared. I'm ignoring the I squared for right now. On the bottom, 5 times 5 is 25. 5 times negative 2i is negative 10i. 2i times 5 is positive 10i. And 2i times negative 2i is negative 4i squared. As you can see, when you multiply the conjugates, the single i's disappear. And since you're going to replace the I squared with a negative 1, the i's will actually disappear entirely. In fact, we're going to replace both of these with a negative 1. So let's see, we've got 20, and then negative 8 minus 5 is negative 13i. 2 times negative 1 is negative 2. On the bottom, I have 25, and negative 4 times negative 1 is positive 4. Continuing to simplify, I get 18 minus 13i over 29. Of course, we need our answer to be in standard form, so split it. 18 over 29 minus 13 over 29, I on the side. And the question, of course, becomes when you split it, do you need to reduce either fraction? There might be something that shakes loose when you split it into fractions, and you need to make sure that you take care of that. All right, so that is your basic operations. Add, subtract, multiply, and divide. Okay, I'm going to flip the page. Roman numeral 3. Now we're going to do a problem where we're going to find zeros that are complex. So we're going to factor f of x, and we're going to use rational zeros theorem. And we're going to end up with complex numbers. All right, so for example, let's say that f of x is the polynomial x cubed minus 3x squared plus 4x minus 12. Okay, so following rational zeros theorem, you want to start by listing all zeros, p over q, all factors of the zeros. So factors of the zeros, excuse me. You want to make a list of all possible zeros. So p is always the last term. So 12 could be plus minus 12, and 1, 2 times 6, 3 times 4. This one, the coefficient is 1, so plus minus 1. So our list of possible zeros is each of these over 1. I'm going to put them in order as long as I'm at it. 1, 2, 3, 4, 6, and 12. There's our possible list of zeros. Okay, so now we're going to test to find zeros. And again, I like to start with 1. So I'm going to find f of 1. So 1 cubed minus 3 times 1 squared plus 4 times 1 minus 12. 1 cubed is 1. Minus 3 plus 4 minus 12. And you can just tell that's not going to be 0. So 1 is not a 0. Okay, let's try a negative 1. So we get negative 1 cubed minus 3 times negative 1 squared plus 4 times negative 1 minus 12. So I get negative 1 minus 3 minus 4 minus 12. No, that's definitely not going to give us anything. So, and I'm just going to try a 3. F of 3. So I've got 3 cubed minus 3 times 3 squared plus 4 times 3 minus 12. So that's 27 minus 27 plus 12 minus 12, and we have a winner. Okay, so we tested to find the zeros. Now we're going to divide out the 0, which in this case is x equals 3. I'm going to use synthetic, so 3 goes in the corner box. And I want the coefficients, so it's 1, negative 3, 4, and negative 12. Double checking, it goes 3, 2, 1, none. So I don't need to fill anything. Skip a line, draw a line, and we're going to divide out. 3 times 1 is 3, negative 3 plus 3 is 0. 0 times 3 is 0. 4 plus 0 is 4. 3 times 4 is 12. Negative 12 plus 12 is 0. Again, if you don't get 0 for the remainder, then you have a bad 0. It's not a 0. So at this point, what I have is f of x equals, I divided out a 3, so there's a factor x minus 3. And what I'm left with is, and so we started with a cube, we divided an x out, so this is an x squared. So this is your x squared. There is no x term, and 4 is your number term, so x squared plus 4. That's what I have so far. I guess I should number these steps. Okay, so list the possibles, test to find the zeros, divide out the zeros. That's what we've done so far. Okay, so now we're going to go one more step. Obviously, x squared plus 4 doesn't factor. So if a quadratic remains, we can use factor or use the quadratic formula. Obviously, x squared plus 1 doesn't factor. So the nice thing is if you don't have an x term, you can just solve by taking square roots because there's no x term. If there is an x term, you have to use the quadratic formula. As it is, I can take x squared plus 4 and just solve it by extracting square roots. So x squared equals negative 4. Take a square root of both sides. 2 x's, 1 comes out. It is positive and negative. So with the negative 4, just to show you a step, you probably won't need to show on your own work. It's 2 times 2 times negative 1. So 2 2's, 1 comes out, and I have square root negative 1 left. That gets replaced by an I. So plus minus x equals 2i. So x equals plus and minus 2i. Okay, so our zeros are 3, 2i, and negative 2i. So the factorization is f of x equals x minus 3, and then I've got x minus 2i and x plus 2i. That is the factorization. All right, so let's graph this and see what it looks like. So we're going to take and we're going to graph the polynomial that we ended up with. Let's rewrite it here. F of x equals x minus 3, x minus 2i, x plus 2i. Okay, so if you were to multiply this out, the leading term would be x times x times x. It would be x cubed, which is a cubic. All right, so what do we know about this? Let's analyze. It's a cubic, so it's an odd degree, which means it's an S shape. The leading coefficient is a positive 1, so it's going up. Okay, so it's going to be an S shape going up, something like this. Now, here's where the zeros come in. Only real zeros show up on the graph. So only the real ones show up. So x equals positive 3 is going to be the 0 or the x-intercept. Typically, the imaginaries will create bumps, but those aren't really critical points for what we do. So if I had to do a sketch of this graph, I know it's going to cross at 3, 1, 2, 3, so that one's kind of a no-brainer. The question is, what are the critical points that we actually need to graph? So we probably need to find the y-intercept. So you're going to set x equal to 0 and solve it. So x equals 0. We end up with negative 3 times negative 2i, which is 6i, times 2i is 12i squared, which is negative 12. So it crosses way the heck down here. I'm going to make this a little more. 2, 4, 6, 8, 10, 12. Crosses there, and we're assuming from there it goes on. And multiplicity-wise, x equals 3 only appeared once. So it had a multiplicity of 1, which means it's a cross, not a kiss. All right, so that's what our graph ended up looking like. Again, the imaginary numbers create little bumps sometimes in the graph, but they don't actually affect the critical points, which are the intercepts. Those are the ones we're most interested in. Okay, that is the end of the notes. I hope you learned a lot. Have a good afternoon.